Thank you. Wonderful to be here. And time starts right now. So I'll do my talk in the wrong order, right? Just to show you that things are always not happening in the right order. So let me just start with this. So I'll start with towards the end of my talk. I'll show this to you again. So this is just showing you that if I could record each one of your brain right now, and I could understand what was the fMRI signal, I could tell you what you're thinking about. Right. So here, what you see in the ground truth, this is someone in an fMRI machine is being shown this image. We are recording the brain signal. We're using that brain signal to reconstruct, to synthesize a new image that the AI thinks this person is looking at. So the top row is the actual ground truth, and the bottom row is what gets reconstructed based upon the brain recording and with an AI. So this is something that can be done now. We have no idea what will happen when you are in college, when you go to graduate school, when you do your own PhD. You will do a lot more than what has been done. So I just want you to note that this is the ground truth, just to understand. Someone is looking at this image, they are in the machine, we're recording their brain signals, and we're asking, can we build a machine learning method that using that brain signals is able to synthesize the specific image that this person is looking at? So this is the actual image. This is what we synthesize, an actual image, what we get synthesized. So you should be able to see that they are very much alike. And this work was done, I would say, about 6 to 9 months ago. And since then, this has been used by multiple different, so there are a number of different research groups that have also looked at it. And this idea of trying to look at the brain signals and try to reconstruct what is being shown has also been, there was a paper in Nature that came out 2 months ago that was trying to look at a story that was being read to someone, and the brain signals were being recorded. And the question was, can we use the brain signals to recreate that story that person was reading? So one can go from an image to brain signals back to the images. One can go from an image, from a piece of text, from story to brain signals back to a story that is being synthesized. Now, so this is the extent of, now let's go back to the beginning. So I just wanted to set up this context of where we are headed, right? So if we are out of time, at least you'll know this slide. All right, so let me go back to where we are headed, right? So this is the kind of data that one gets in the area of the brain signals, right? So you have, you can record in an fMRI machine the structure. What does a brain structure look like? So that recording will be something like that. Based upon that, you can build a network in terms of which are the pipes of neurons that are linking one area of the brain, your area of the brain, or my area of the brain, onto the next area. And then you can also be giving this brain some kind of an impulse, which could be an image, or you ask this person to do a specific task. There are these signals in the brain that are being firing up. So there are some areas of the brain that are lighting up, and as a result of that, you get a map of the functional connectivity which areas of the brain are firing at the same time. So once you have all of this data, there are a number of different questions that arise. For example, how can you integrate the vast amounts of data that is coming in? Questions about, can you use this data to probe into the brain? Can I understand what does a brain structure look like? Can I understand what does my brain look like, right? If I was to become smarter, what would I need to do in order to make myself smarter? Maybe there is a hint, right? Then there's questions about, can we devise AI and machine learning based upon the principles of how the brain has been built, right? So you would have looked at large language models, and you would have seen that the amount of parameters that these take usually exceed 1 trillion. And of course, a child, by the age they are 2, they are already able, without an extensive amount of training, they can do a lot. And they have not been trained of the same amount of data that a large language model has been trained with. So how do our human brains, how can they learn to do things with far less amount of data? And is it to do with how the brain is structured? Is it to do with how the learning is actually happening? So all these questions about, can we understand the brain so that we can inspire new areas of deep learning based upon how the brain has been structured, right? And then this area of brain and human interaction. Once you develop an AI model, when you develop a machine learning model, this machine learning model will be interacting with a human or with a group of humans. For these interactions to work out well, the AI, the machine learning model, needs to have a model of the human brain so that you can understand, and for those interactions to be effective, that ends up being needed, right? So, so from brain to deep learning, so this entire area of deep learning was prompted by people started looking at, can we build a model for how a neuron fires based upon how the neuron in our brain fires, right? So this journey started in 1943, so about 80 years ago. So people tried to build very simple models of what a neuron, based upon what is the neuron in our brain. And this journey continued, and I would say in the 1980s, this area kind of went into a lull. There was work that had been done, but it was not until, I would say, about 8-10 years ago that this area got a big lift. It was because of the amount of data, the kind of hardware which was out there, it could process it at a much higher scale. And now we have this entire area of deep learning, which has been successful in terms of images, in terms of text, video, and my own area of interest, which is graphs and networks. So it has become immensely successful over multiple kinds of data, right? And then there's also been, now once you have this deep learning enterprise, and once you have the methods that are working with deep learning, there has been work on applying deep learning methods to try to understand the brain structure itself. Is it possible to do? Can we understand the different regions of the brain? And the part of the brain that has been looked at most is the visual cortex, where people have tried to understand the different layers and how this brain processing happens, and so on, right? And then this emerging area of brain-AI interactions, either trying to do an interaction between an AI and the human using text, voice, or in some cases, just looking at a neural implant which should be in the brain. And for that to be successful, you need to be understanding what does the brain circuit actually look like, right? So all of these areas, and let me just try to there are a number of different gaps that exist in terms of our own understanding of deep learning, our own understanding of the brain. And of course, one big area is how does learning actually happen in the brain? So the learning that happens in the deep learning on the machine is based upon gradient descent, and is based upon backpropagation. It's not clear at all how does the brain do its effective learning. And there have been a number of different models that have been put forth in terms of trying to understand how is it that the brain actually does its learning, right? The machine learning methods that are out there, the machine learning methods can be attacked very easily. So you would have seen cases about where a sign that says speed limit or a stop sign can be fooled. A machine learning method can be fooled in thinking that a stop sign is actually a speed limit, right? Using just a few changes in the image. The human brain is much more robust. So there are questions about, can we improve the robustness of the machine learning based upon trying to understand why our brains more robust than the machine learning models. And questions about, can understanding how the brain architecture is, can that lead to modular deep learning architectures that are less data hungry, right? So let me just take you through a couple of examples of my own work, and then I will go to the main area, which is trying to reconstruct the images, right? So the first part of the work that was looking at was, can you understand? So I talked about two different kinds of networks. I talked about the brain structural network that stays, and it's mostly static. It does change as we age, but it's mostly static, right? And then you have the functional MRI that is responding to every task that we are doing. So there are always these questions about, how does this functional MRI work? How does this signaling work on top of this hardware which is out there on the brain? So think about this hardware as your laptop, the circuit that is out on your laptop, that is defining what is feasible. And what is over here is the software that runs on top of your hardware. So somehow this hardware has been optimized so that it can be working with many different kinds of software, and it's more effective. So you want to try to understand what is this coupling between the software and the hardware. There are questions about, can you reconstruct one network from information on the other? So if you had, for example, human subject pairs, and they were doing the same kind of a task, if I'd observe these two networks on one person, and I just observed the other network on the other person, can I reconstruct either the functional network or can I reconstruct the structural network? So can I understand how is this coupling happening between the structural network and the functional network, right? And to try to explain this. So when you're trying to solve this specific task, this is a part of the structural network that is becoming active, right? Then we also looked at some other work, which was looking at, you want to find a network representation of the different processes. So if I go through trying to do different tasks, I want to understand which are the voxels or which are the regions of the brain that are becoming active in terms of trying to solve a specific task, right? And then there are these questions about the functional activity. And when you're trying to do a specific task, the functional MRI within seconds is changing. And you want to be able to understand what is the dynamics of the signal, which parts of of the regions, which parts of the voxels are becoming more active in the beginning, which parts are becoming more active in the end. So you want to understand what is this dynamics of information as a specific task is being done. Right? So now with that, let me look at the final thrust, which is looking at how are we able to reconstruct this image. Right? So here what we looked at we looked at the fMRI, and as you can see, there are a number of, so we wanted to get tasks in which people were being shown some images, and we needed to have a recording of the brain. Right? So the more recent data set was what is called the natural scenes data set, and the images that people are being shown come from a well-established cataloged set of images called COCO. And then after that, what you have is there are 8 human subjects. And I want you to understand how sparse that data is. So in neurosciences, you have the cost of doing a human subject study is immense. You cannot collect data on text and images like you'll have on your cell phones. It's very difficult to collect this data. So you have data that comes from a very few human subjects, but this data is very deep. You have collected a lot of deep data on a specific human subject. And there is this question about if you have collected some deep data, can you use this to build models so that if I go, so here this data set has got subject on 8 human subjects. So obviously the question arises, if I built a good model and if I made good use of this data set, perhaps for the 9th subject, I don't have to have fMRI recording over a month. Can I just do an fMRI recording over a day or over a few hours, and can I build a good model? Right? So you can see that there are 8 human subjects. There are 73,000 images. Let's say you take one human subject and you're showing this human subject one image. You at least need a few seconds. So in 1 hour, maybe you can be doing maybe 100 images, maybe 150 or 200 images. In 1 day, maybe 1,000, 2,000, maybe 1,000 images is the maximum you could be doing. So if you wanted to bring in someone for 1 week, 5,000 images. If you wanted to collect 20,000 images from one person, 1 month. Right? So the data set is very rich, but it's very difficult to collect. Right? So it's wonderful that someone actually collected this data. And not only that, they made the data set where they repeated the same image 3 times. So the same subject was shown the image 3 times to get the recording of those images. So now we have this data set, and this image comes, so we have so this is what this data set looks like. So we have an image, that is the subject is being shown, the fMRI signal that is being produced in the brain, and we have a text caption that comes with the image that describes what this image is. So we have these 3 elements, the image, the text, and the fMRI signal. And with these 3 elements, we have to build a model so that if we are given now just the fMRI images, you have to reproduce that image this subject was shown, right? So and in this case, as you can see, that there are captions of different kind, and and so what happens at the end is that you don't look at the entire brain, you look at a large number of voxels that have meaningful information on that image from the brain, and that is, in this case, is 15,000. So about, let's say 10 to 15,000, 10 to 16,000 voxels of interest. So you're starting with, now your brain signal has reduced to just a spectrum of, let's say, about 15,000 signals. Because on every voxel, you're trying to measure what is this level of activity in that specific voxel, right? So then what you have after that is you build a model. So let me skip this slide. So we build this model which is like this. So we use what is called a clip. It connects images to text. And you get to a joint space in which you store information on images and you store information on text. And this is a joint space. So what we end up doing, let me show you this, this high-level diagram, is you have a human which is being shown an image. That leads to a signal, and you get to the fMRI signal after that. Once you get to this fMRI signal, we learn how to map it to this joint space of text and images, the clip space. So the only modeling that we do is how do we model this fMRI data into this joint clip space. Because once we get to this joint clip space, once you have learned this mapping, if I'm given a new image, if I'm given a new fMRI signal, I can use that mapper to go to this joint space, and I can generate a new image from that joint space. So this joint space gives us enough information to generate a new image from that space. Right? So that is the overall design. We learned how to map the fMRI signal into a joint space that contains information on the images and on the text. Given a new fMRI recording, which is being shown on the right side of the screen, we can use the same mapper to go to that joint space, and now using models that are trained in the joint space, we can learn how to generate new images, right? So when we go back to this example, what has been done is that we take the ground truth image. Every ground truth image has been mapped. By learning how to doing this mapping, we learned a robust way to take any fMRI recording and go to this joint space, right? And then later, when you want to test this method out, you take the fMRI recording, you go to that joint space, and you can generate a new image based upon that. So that is the essential idea, right? So let me just take you through, right? So this gives you more cases of when it works well, when it doesn't work that well. So here is the top row is the ground truth stimulus. The bottom row is what we reconstruct, what the AI synthesizes by looking at the fMRI signal, right? So you can see that there is a pretty good correspondence between the top and the bottom. When there are details that are close up, or when the AI model is being presented new semantics, then this model will not do as well, right? So this is bad when, right? It is not perfect. And here what you should note is that, remember I told you that the same image was being shown 3 times to every subject. So the question arises, if I took those 3 fMRI signals and we try to synthesize a new image from each of those signals. What is the outcome? And this shows you that for this actual image, you look at the 3 fMRI signals, and you attempt to synthesize. These are the 3 different images that the system is going to synthesize. So not exactly the same image, but they're close to the actual image which is being shown. If you're shown this, and there were 3 fMRI signals, using those 3 fMRI signals, these are the images that will be synthesized. And we have compared this with other work which exists, right? All of this data is essentially showing you that the clip, using this joins space in which you're trying to collect information on images and text, is useful. Why is it so? Because the text contains information on the semantics. So you need to be looking at both what is the semantic content, and you also need to be looking at how is the image realistic or not? Is it a natural image or not? And going to this joint text image space lets you do both, right? So I'll not get into these results. The other thing that you should see is that, so it's possible to define measures based upon how realistic this image is, and these are our scores. You can look at these questions about if you have images that have different kinds of objects in them, you can ask, if the subject was being shown an image with 5 different kinds of objects, do the synthesized images now repeat that? Can they construct images with 5 different kinds of objects? And this is what is measuring that, and it just shows that if you were to vary the number of different types of objects from 2 to 50, this is how accurate our system is, right? So just kind of a summary of where we are. We have just given you an overview of it. This is some ongoing work which is in the lab right now. There have been a number of recent follow-on works, including what I mentioned from brain signals to text. And Nature, the journal Nature had an article, mind-reading machines are here, is it time to worry? So there are just questions about ethics and about whether it's being used correctly or not. Overall summary, a lot of data, questions about how do you build these models, how do you transfer models from one person onto the next. And with that, I'm going to stop. Thank you.